Hello everyone. What we're going to talk about today is complex numbers. And from starting in elementary school, you were spoken to about how your numbers are classified and grouped. So just with the little diagram that I sketched, you have whole numbers, and integers also contain whole numbers. Then you have rational numbers, and they contain the integers and whole numbers. And rational and irrational numbers are what make up uh, rational and irrational make up your real. So, on the contrary of that, then you also have imaginary numbers. In imaginary, you have the number I or 4I, or what we're going to build up to and talk about is the complex notation A plus BI, where BI is our imaginary portion, A would be the real portion. So, within math, there's a lot of philosophy. For years, centuries ago, there was debate on negative numbers and the number zero. And can you imagine what it was like with the imaginary number? And a way to which to be able to think about this is that as people were solving quadratic equations, they were getting solutions that had a negative sign under the radical. And this is not a real number. Okay, so the square root of negative 1 is not a real number. Yet when solving some quadratic equations, we can get this as an answer. So how is the square root of a negative 1 not real? Well, if we were just to look at and say, okay, well, let x equal the square root of negative 1. And the principles of square roots, if we looked at that and squared both sides, that would remove the radical, and we would be left with x squared equals a negative 1. And this is an untrue statement. I cannot square a number and get a negative answer. It goes back to a negative times a negative is a positive. Whenever I have an even number of negative signs, I get a positive answer. A positive times a positive is a positive. So I cannot multiply the same number by itself, irregardless of its sign, and get a negative answer. And that is where the imaginary number I comes into play. The number I, as we'll go through, I is equal to the square root of a negative 1. Or if I square both sides, I end up with I squared equals a negative 1. And how do I use this? For instance, I'm given the problem, the square root of a negative 25. I can break that down into a product. I can say negative 1 times 25 under the radical. And then I can separate that radical to where I have the square root of a negative 1 times the square root of 25. Well, the value of the square root of a negative 1 is I, and the value of the square root of 25 is 5. I write the number I as though it's a variable. I write it after my numeric value. Okay, go ahead and pause the video and work these two problems, and let's see if we get the same answer. Alright, so for the square root of a negative 49, I do the same thing, except I'll take a shortcut here. I already know that this is going to be this times this. Negative 1 times the square root of a negative 1 times the square root of 49. And I know what I get is I times 7. And that leaves me with 7I. And for the square root of a negative 3, same thing. And that is my answer for that one. Powers of I. Powers of I are cyclic. It's like a clock. And it keeps working its way back around. 1, 2, 3, 4, and then back to 1, 2, 3, and 4. We've talked about the first two, about I and I squared. I cubed is equal to a negative I. And this shows you the logic behind it. Well, I can say that is simply I squared times I. I squared has the value of negative 1. A negative 1 times I is a negative I. For y to the fourth, I view it as my rule for powers of powers multiplied together, so therefore I can break them down. So that is I squared to the second power Well, I squared is a negative 1. Negative 1 squared is equal to 1. Again, my powers, they work almost like a clock. So once I go to 5, I to the 5th power, I view that as the same value of I to the 1st power. I to the 2nd power is the same as I to the 6th. And we'll look at that and the rules behind it. So let's take a look here. And see. So continue talking about the powers of I. What you'll do, this secured, divide the exponent of I by 4. So whatever the exponent is, if you divide it by 4 and you get no remainder, then the value of that problem is going to be equal to 1. It's considered to be just like I to the 4th. If you divide the power that is with I and you end up with the remainder of 1, then you treat it just like it's I. Your value is going to be the square root of a negative 1. End up with the remainder of 2, then you treat it like it's I squared. A remainder of 3, then treat it like it's I cubed. So the very first one, if I look at this, now remember that division, I'm telling you to divide, is the same as subtracting. It's just a faster way to subtract. It's just like multiplication. Multiplication is the same as adding, except it's a faster way to add. So whenever I look at this and I say, okay, 5 divided by 4, and I'll sketch that out right here. I know that it's 4 going there one time, and I have a remainder of 1. So a remainder of 1 gives me the value of I. And just looking at this, like I said, it's like a clock. So 1, 2, 3, 4. I'm to the 5th. So there's 1, 2, 3, 4. The 5th one, I'm back at 1. Okay? So I to the 5th has the value of I. Go ahead and pause the video and work the next 3, and let's see if we get the same answers. Alright, so for I to the 7th, I know that I'm going to have a remainder of 3. So a remainder of 3, then my answer is going to be equivalent to a negative I. I to the 16th, well, 4 will go into 16 4 times. There is no remainder. So then what I to the 16th equals is 1. I to the 26th, 4 will go into 26, and we'll write that out. How many times will 4 go into 26? 6 times. So I get a 2, so I have a remainder of 2 there. For a remainder of 2, my answer is I squared. Real quick to make sure that you understand, because if you can visualize this, then it's remembering rules goes away. So there was 1, 2, 3, 4, 5, 6, 7, right? I to the 7th, so that brings me back around to the 3rd. So I to the 3rd power is a negative I, negative I. So the powers of I, again, it's cyclic. Okay, so to wrap up, we finally get to complex numbers. The complex number is a composite. It's made of a real number and imaginary. A is my real portion, and BI is my imaginary portion. And it's easy to look like this falls in line with all of our everything we've been talking about. Whenever A is equal to 0, we just get a pure imaginary number, BI. And whenever BI is equal to 0, we end up with just A and a real number. You will not have to do this, but I wanted to be able to let you know with the Argand diagram, what you can do is you can graph complex numbers. Your x-axis is viewed as the real axis, listed as R. Your y-axis is the imaginary axis, listed as I. And you graph A plus BI by just graphing first the A and then the BI. Something for you to know. As you move up in higher level math, you will do that. Okay, guys, continue to watch the videos from the publisher, structure, critically think about your homework. Work the problem as many times as you need to where you can say, I know how to do this. Good luck with your homework.